Hey guys, welcome to our video. Today we'll be talking about our Microcontrollers Final Project here at Utah State University. My name is Drew Hogan.
I'm Tommy Severson. And right here we have the Min EV, which is a small, user-friendly, self-driving vehicle. So a couple quick key features about this project is this keypad here for the user input. It's 2 stepper motors to drive and turn the vehicle.
As well, a portable charger to supply 5 volts to the microcontroller, and of course the microcontroller to control the logic. While designing our final project, we came up with 4 main requirements we wanted to implement in our car. The first of which is we wanted it to require user input. To achieve this, we configured a keypad on our car in which the user will enter a distance followed by a command. The different commands are forward, backwards, left, and right. So for example, the user might enter, I want to go 1 foot forward and then 18 feet to the right. Once the commands have been entered, the user enters the pound button, and after a short delay, the car will execute the given commands.
The next requirement we came up with is we wanted this car to be fully autonomous, meaning after the user hits that pound key, like Drew said, all the commands and distances will be run without the operator needing to do anything else.
Next, we wanted fine motor controls. So in order to execute the commands such as turning a complete 90 degrees to the right or left, we use a stepper motor. 1 turn of the wheel results in 512 turns of the stepper motor internally. So therefore we were able to accomplish the fine-tuning necessary in our design.
And lastly, we wanted this car to be very reliable. So, and we successfully implemented all these requirements to do so, meaning this car functions perfectly without the user needing to do anything else after entering the right inputs.
In our design, before creating our software, we came up with the following pseudocode. So we begin in our main function by initializing the GPIO ports to run the motors and likewise the keypad. We then enter a while loop, which we will never exit. In this while loop, we check if our state is equal to 0, so we made a simple state machine, then we call a user input function. And then if our state equals 1, then we are ignoring any input in the keypad and we are executing the commands that we're given.
An important function we wanted to go over was our user input function. It starts by collecting a value from the keypad and checking if it equals pound. If it does equal pound, we will switch the state to 1, meaning the car can execute distances and directions. If the value is equal to a command or a direction, it will store that command in this array and the associated distance in the value array. Lastly, if a number is pressed, 0 through 9, or multiple numbers are pressed, let's say 12 for example, it will store that first digit, 1, in this temp variable. Then it'll go through with the second digit, multiply that first digit by 10, so 1 times 10 giving us 10, and add that second digit, which is 2, to give us 12.
When the state is equal to 1 in our main function, we will enter our execute command function. Here we use some variables that were edited in the past state. For example, we will loop through the number of command times, and then we have a switch where according to the command that was given, we execute one of these functions, and we also pass in the value that corresponds with that function. So to demonstrate our project, we've created a simple route. So we'll start the car here, and I have a yardstick in front of me since we're dealing with feet. So the car will go 2 feet or 24 inches forward, and then left it'll go 3 feet, and then right it'll go 3 feet, and then we're going to command it to turn around and do everything in reverse. And we'll see if it gets back at the same spot.
Now we're going to demonstrate what the user has to do to input commands and values and then see it actually run. So first, to follow our route, we want to go 2 feet forward. Next, we want to go 3 feet left, 3 feet right, 3 feet back, 3 feet left, and finally 2 feet right. Next, the user will have to hit the pound key to initiate driving.
We initially programmed our car to go 1 foot forward and to turn 90 degrees based off of 2 things: the diameter of the wheels, which is 12 centimeters, and the distance between the wheels. I will demonstrate the fine tuning that was still necessary by entering in 1 foot forward. As we can see, the car is precise.
After calculating how many rotations needed to turn the motor to make the vehicle rotate 90 degrees, we did some fine-tuning by setting a start point and turning the vehicle 4 times in the same direction. Next, let's talk about our software. Let's start with our main function. First, we initialize the GPIOs by calling motor init and keypad init. This sets up the motor and keypad to be used. Next, we enter a while loop, which checks if the state is 0 or 1. If the state is 0, we can call our user input function, which collects input from the keypad. If the pound key is pressed, then the state will switch to 1. When the state is 1, we enter a for loop that iterates through the number of commands. Next, we enter a switch case statement that takes a look at each command and decides if it should drive forward, backward, left, or right, based on the value entered in feet. Now we'll look at our car.c file with all of our functions and logic. We're going to look at a couple of functions specifically, but let's start with these macros defined at the top. These macros helped us with our distance and turning measurements, and they were adjusted as testing went on. Now in our drive function, we can see these macros being used to calculate the total rotations needed to drive forward a foot. Here is our turning left function as an example for turning, using the same macro above to decide how long to rotate the motor to turn 90 degrees.
In conclusion, our project meets all the requirements that we initially set. However, there are still a couple things we could implement or change to make this more robust or versatile.
We can improve this car by adding something like a Bluetooth control with a separate microcontroller, or perhaps motion sensors to prevent it from colliding with anything. But overall, our project was successful and we are satisfied with the results. So, thank you for watching.